So we're going to do some more examples of determining SN1, SN2, E1, and E2. And then we're going to kind of backfill some of the stereochemistry stuff that we had to skip to get here. So what I want to do first is just kind of go through the hierarchy. I don't know what I just do. Right, the order. There you go. The most important thing for determining what kind of reaction you're going to do is the halide. If the halide does not do a type of reaction, you can't do it. Right. So what I mean is, like, tertiary halides can't do SN2 reactions, right? So you can't end up doing an SN2 reaction even if the rest of the conditions say you're going to do an SN2 reaction, because the halide doesn't do an SN2 reaction. You can't do an SN1 or an E1 reaction on a primary halide, because primary halides can't do SN1 or E1 reactions. So even if the rest of the conditions say, hey, do an SN1 reaction here, the halide says no. So the halide is kind of like your girlfriend when you go to pick out a place to eat. If she doesn't want to go somewhere, you're not going there. They'd be like, hey, you want to get Chinese? And she's just like, I'm not feeling Chinese today. You're not getting Chinese food. No amount of negotiations is going to get you there, right? Then you're like, well, I could have a steak. Can we go to Outback? She's like, I'm vegetarian this week. And you're like, ah! And you end up at Tropical Smoothie hungry. And you're like, oh, thanks for this delicious smoothie, and now I'm hungry. Right? So the halide has veto power. The halide gets to pick has the strongest say in what you do. The next is the nucleophile or base, right? So is it charged / uncharged, right? And then the last thing is the temp. So the halide is most important. The temperature is least important, right? So if you have looked at the halide and the nucleophile and base and decided you're doing an E2 reaction, it doesn't matter if the temperature is below 0, right? That can't override the halide and the nucleophile and the base, right? So if you've done the first two and you're like, I'm doing an E2, temperature doesn't matter. All right, so you just work your way down, and a lot of times you can skip temperature if you've already figured out exactly what reaction you're going to do. So this is a primary halide. And so right off the bat, we can eliminate the ones, right? Because I can't do an SN1 and I can't do an E1 on a primary halide. So I'm down to SN2 or E2. Our big bases, like potassium tributexide, they only do E2 reactions. They can't do SN1, I can't do SN2 reactions. So just from the halide and our base, we know we're doing an E2 reaction. So we don't have to look at the temperature. So it doesn't matter that the temperature is low. We've already decided we're doing an E2 reaction.
I was asked what the other big base is that you know.
LDA. LDA is the other big base. So we're going to make a double bond. So we know we're going to do an E2 reaction. We're going to make a double bond. Here I have a next one is a tertiary halide, right? Tertiary halides can't do SN2 reactions. So right off the bat, I eliminate SN2 as an option. As he writes an S. Right? Now I look at my nucleophile slash base. Is it charged or uncharged? It's charged. It has a metal on it, so it's charged. So that means I get to eliminate the ones. Again, I'm doing an E2 reaction. And again, the low temperature doesn't matter because I've already settled on my elimination before I get to the temperature. Secondary halide, so I can do everything. Is my nucleophile charged or uncharged? Nucleophile slash base, charged or uncharged? Charged again. So I get rid of the ones. Now I have either substitution or elimination left, and I have a low temperature. So that means I'm going to do substitution. Low temperatures are substitution. So 0 degrees and below is substitution. 20 degrees, or in the notes it says room temperature, which is roughly 20 degrees, give or take, and above are eliminations. So this is an SN2 reaction. What is the big thing we have to remember with an SN2 reaction? Right, we invert our stereochemistry. So not only here do you need to make sure that you add the right group, right? You add the nucleophile, the correct nucleophile. You also need to make sure that you give it the right stereochemistry. So my leaving group is back. That means my nucleophile is going to be, okay, apparently I'm not going to be able to write that in there. Try again. Come on. Daddy needs an O. There you go. Is going to be forward, right? You're going to invert your stereochemistry. Now, I will tell you on the exam right now, if this was the exam question, you would have all these options, right? So it wouldn't be just enough for you to get the nucleophile right. You'd also have to make sure that you knew that you inverted your stereochemistry. Right, so you're going to get tested on both.
The question was, how do you know that you have to invert your stereochemistry for a reaction?
So because it's an SN2 reaction, they always invert their stereochemistry. Right, the nucleophile has to come from behind the leaving group to push it off. So if the leaving group is back, behind the leaving group is coming from the front. If the leaving group is back, coming from behind it, it's coming from the front. If it's forward, it's coming from the back. That makes sense? Sure. And I kind of fumbled it at the beginning. All right, tertiary halide again, SN1, E1, E2. Is water charged or uncharged? It's uncharged, right? There's no metal on it, should be uncharged. So we eliminate our 2 right off the bat. 100 is greater than 20. Thank you, Sesame Street. So that means I'm going to do an elimination. So I'm going to do an E1 reaction. So what kind of reaction am I going to do in the first example? Going to do an E1 reaction, right? Secondary halides can do everything. Then I have an uncharged nucleophile or base, so that gets us to the 1s. And then high temperature is going to be an elimination. So this is going to be E1. And then I'm going to pretend like I have enough space here. Which one is the right answer? It is not C. It is B. Now, what? It's B because you make the carbocation. I'm going to go over a slide so I actually have space to draw this. Right, so give me one sec. Wait, no, as I say it's B, and then I drew C. Good job. Good job. Your tuition dollar is hard at work. So, make my carbocation. Every time you see a carbocation, you should think, huh, can I rearrange this? Is it a secondary carbocation? I can move a methyl group, I can move a hydrogen. Move that hydrogen over. Now I have a tertiary carbocation, right? You can treat this as your alpha, beta 1, beta 2. Which beta carbon am I going to make my double bond towards? It's going to be the one that has the least hydrogens on it. So that's going to be beta 1. So that's going to make that product. So just be mindful when you do SN1 and E1 reactions that there's a possibility that you can get a rearrangement.
I was asked, how do you know if your reaction is going to make a carbocation?
If it's doing an SN1 or an SN2 an SN1 or an E1 reaction, it's going to make a carbocation. So both ones make a carbocation. All carbocations can be rearranged. So if it's a secondary carbocation, you have to look and say, can I move a hydrogen or a methyl group from beside it or do a ring expansion to get from a secondary to a tertiary carbocation? So anytime you have a secondary carbocation, there's a chance it can rearrange. You just always have to check. What type of reaction do we have down here? E2. Right, so now that's going to be our product. Right, because now you're just following your simple, like, I know it's E2, I have an alpha, I have beta, scribble, beta 1 and beta 2. Make my double bond to the beta carbon that has the least hydrogens on it. Yes, sir.
I was asked if we ever use the protic or aprotic solvent to determine the type of reaction.
No, the protic and aprotic solvents, they're kind of paired together, right? So an aprotic solvent is going to be with a charged nucleophile, and a protic solvent is going to be with an uncharged nucleophile or base. So looking at the nucleophile slash base is also kind of the same as looking at the solvent. So I just think it's easier to look at the nucleophile. So if you looked at the old exams, they were all kind of set up where they had a box that was like type of reaction, and then some super cool reaction, right? And you had to figure out what the reaction was and then the product. Right, so this would be SN2, and I'll make sure this is clearly a wedge. Clear the wedge. So then my product is, I want to try to recreate that same kind of question, the same kind of way on the exam. So what I've done is I've broken every one of these types of questions into two parts. So when you take the exam, you're going to have something that is like, right, so you're going to have your reaction, right, and then under it, you're going to have, right, multiple choice, pick the reaction, right, and then immediately under that question, the next question is going to be the exact same reaction, with then possible products. Bless you. You get the gist, right? And so then you have to first pick the type of reaction. What type of reaction is this? E2, right? Then, and the question right under it, you're going to then use that knowledge to then figure out what your product is. That's the best way I can figure out how to do it. Be like, oh, that's my product. There are, instead of your classic 4 multiple choice answers, there are 6. There's basically always 3 elimination products and then 3 substitution products that kind of cover all the options of SN1, SN2, E1, E2. But it doesn't have the crazy undergrad answers where you just like randomly throw metals on your molecule and just do crazy stuff. I couldn't get that creative. I'd have to start drinking, I think. Like, I don't know, like a handle of Jack, and I'd be like, oh, I've channeled my inner sophomore organic chemist. Ah! But I wasn't quite there. So that's what it's going to look like on the exam. It's just going to be basically 4 problems a page. What's the reaction? What's the product of that reaction? What's the reaction? What's the product of that reaction? Then you're going to go on to the next one. So I'm trying to keep it as like organized as I can without turning it into like a 35-page exam. Right. So does that seem good? You guys all feel like you can pick the type of reaction and then figure out the product based off of that? Cool. So I'm going to circle back to the stuff I skipped before to get us here, right? And that's going to be the stereochemistry in eliminations. So what this lets us do is the R or S of the alpha and beta carbon can be or can determine E or Z in eliminations. So if we have if we have stereocenters on both alpha and beta, we can use that to determine if we're going to make the E double bond or the Z double bond. So to do this, we need to talk about the types of eliminations we can have, right? Not types in terms of E1 or E2, but like kind of mechanistically how they happen. So first is the anti-eliminations. And anti-eliminations are the eliminations you think of when you do an E2, right? So your leaving group and H must be on opposite sides. So if you're doing an E2, you only do anti-eliminations, right? E1 can do these, right? E1s are weird. We'll talk about it in a sec. The other type of elimination is a syn elimination, where your leaving group and hydrogen are on the same side. Only E1 reactions are able to do this. So E2 reactions only do anti. E1 can do both syn or anti eliminations. So, right, the anti is just like we saw before, leaving group, hydrogen, they're on opposite sides. You do your elimination. Syn, leaving group, hydrogen are on the same side, you do your elimination. Right, the reason E1s can do both is that E1s, the first thing they do is they lose the leaving group. Right, so they lose the leaving group, so you can do both. So what happens when you do an E1, right, is you have your leaving group, you have your hydrogen. Step one is your leaving group leaves. And that generates a carbocation and a hydrogen. Now, the only thing that has to happen for this elimination to occur, right, so is it your H and, it's really bad, and your p orbital must line up, right? So your p orbital is sitting in the plane of your screen, right? And now you just need your hydrogen to line up with that p orbital. So it doesn't matter if your hydrogen is lined up with the bottom half of the orbital or if it rotates around and lines up with the top part of the orbital, right? As long as that hydrogen is in the same plane as the p orbital, you can do the elimination. So if the hydrogen lines up like this, it looks like you've done an anti-elimination, right? Where your leaving group and your hydrogen were on opposite sides. If it lines up like this looks like you did a syn elimination, where the leaving group and the hydrogen were on the same side. So these two different mechanisms, right? Since E2 only does anti, different diastereomers lead to different E/Z outcomes. E1 says it can do both, different diastereomers. Different diastereomers are going to lead to the same product. So we're going to do some examples because I know words suck, pictures are better. That's why no one reads books anymore. All right, so let's say we're doing an E2 reaction. Right. The main rule for an E2 reaction is that you have to have your hydrogen and your halogen on opposite sides, right? So if you look at this, my hydrogen is back, my halogen is forward, right? This is alpha, this is the beta carbon I'm going to want to eliminate from to make the most substituted double bond. They're on opposite sides, so this conformation of the molecule can do an elimination reaction, right? Can do an E2 in this conformation. Now, what you want to look for here is right here. This is where my double bond's going to be, right? Well, right now, my methyl group, this methyl group right here, and this ethyl group are on opposite sides of that bond, right? So when I make the double bond, they're going to be on opposite sides of that bond, right? They're trans to that single bond. They're going to be trans to the double bond. And then I can just fill in my methyl group, and that's my product. Now, if I make the diastereomer of my starting material, so if let's say I have bromine back, everything else is the same. Still doing an E2. Here's my alpha. Here's my alpha. Here's my beta that I'm going to eliminate from. When I check, my hydrogen and my bromine are both back. They're on the same side. So this conformation of this molecule can't do an E2 reaction. What needs to happen is I need to rotate around that single bond so that my bromine and my hydrogen are on opposite sides. So if I rotate around, squiggly arrow, now my hydrogen and my bromine are on opposite sides. Right? If you don't believe me that I just turned it, we can check the E and we can check the R and S. So bromine's 1, this is 2, this is 3. This looks R, but it is S because the hydrogen's sticking out at us. Right? 1, 2, 3. This is also S. So I didn't change the chiral center at all. I just turned the bond. Now this is the conformation I can do my elimination in. here's where my double bond's going to go. Now, this methyl group and this ethyl group are on the same side of that single bond. So they're going to end up on the same side of the product. So changing the chirality of one of the either alpha or beta carbons is going to change your double bond geometry, because you have to change the orientation, the conformation of your molecule to get your hydrogen behind your leaving group. E1 reactions, we don't have to worry about this. So regardless of what your starting material is, E1 reactions always put the large groups on opposite sides. So you want your large groups trans in your product. This leads you to making the most stable double bond. So let's say we have there you go. All right. So all you have to do now is you're like, okay, I'm doing an E1 reaction. What I want to do, regardless of my stereochemistry, is right here's where my double bond is going to be. I want to put the two large groups, which in this case, ethyl is the largest group on each carbon. I want to put those two large groups trans to each other and then fill in the other carbons in the product. Right, so you're just identifying the two large groups regardless of the stereochemistry on your alpha and your beta carbon and putting them on opposite sides. So it doesn't matter what diastereomer you start with, you always just end up putting them on opposite sides. And the reason for this, the reason this happens is, what's the first thing you do in an E1 reaction? Is you pop off your halide, you pop off your leaving group. When that happens, should I draw the right product here, the right compound? Right, I break off this. My carbon, my carbocation, no longer has stereochemistry, it's flat. Right, so now the hydrogen is just trying to line up with that p orbital and when it lines up, it wants to put those two big groups as far apart as possible to like minimize gauche or eclipsing interactions in the Newman projection. And that's what's determining what our product is hey, I can line up, that hydrogen can line up either with the ethyls far apart from each other or close to each other. And when they're far apart, it's more stable. So it's going to line up so those ethyl groups are far apart. That's it. So far, so good. Then we can do eliminations, the stereochemistry of eliminations in rings. We touched on this slightly previously. So I can't rotate all the way around a single bond when I'm in a ring, right? So that means I'm kind of limited to, I can't change my conformation enough to get my hydrogens to be on opposite sides if they're not already. So what I mean is, right, if I have this, oops, these are the conditions to do an E2 reaction, right? So I'd be like alpha, beta 1, beta 2. And you're like, oh, I've got to follow Zaitsev's rule. I want to make the most substituted double bond. I want to make my double bond to beta, it's crappy, but beta 1, right? But you have to check, to do an E2 reaction, I have to have my hydrogen on the opposite side from my leaving group. And here, my hydrogen and my bromine are on the same side. I can't turn that single bond all the way around to put them on opposite sides. I just can't do the elimination to make to beta 1 now, because there's not a hydrogen that's on the opposite side of the halide at beta 1. So what I have to do is I have to do the elimination towards beta 2. I'm going to move my beta 2 for a second. Right, there are two hydrogens on beta 2, right? One is a wedge that I can't remove. The other one is on a dash that's on the opposite side from the halogen. So that hydrogen on beta 2, the one that is down, is the only hydrogen that I can eliminate using an E2 reaction. So the product I'm going to get is that, where I wouldn't do anything to the stereocenter at beta 1, but I'd make a double bond between alpha and beta 2. Yep, so that's what I was just getting ready to do. So if I did this, right? If I did this and did the exact same thing, still an E2 reaction, alpha, beta 1, right? Beta 1's where Zaitsev's rule wants you to put the double bond, and now your hydrogen is on the opposite side from the halogen. So now you can make your double bond there and get the product that you would expect from Zaitsev's rule. Right? Zaitsev's rule is still telling you to make the most substituted double bond, but if you can't, then you just make the next most substituted double bond that you can make. It's like, oh, it's kind of like if you had no hydrogens on beta 1 up here, right? You'd be like, well, I can't make a double bond there because there's no hydrogen I can remove. It's the same thing. There's a hydrogen there, but you can't remove it because it's on the wrong side of the molecule. Now, let's say we're doing an E1 reaction. E1 is like the honey badger. He don't give a bleep. He's just going to make the most substituted double bond that he can. So you're just going to strictly follow Zaitsev. We're going to be like alpha, beta 1, beta 2, beta 3. Which one has the least hydrogens? Beta 1, making my double bond there. Oh, I changed the stereochemistry? Don't care. Make the most substituted double bond. So if you're doing an E1, the stereochemistry really doesn't matter, right? Because the first thing you do is you lose the stereochemistry on your alpha carbon and make it flat and put a p orbital there. Then you just have to line up your hydrogen and it can eliminate. So what type of reaction am I doing on the first one? E1. Right? Now the product here is going to make you angry. It's fine though. The product ends up being this. Because, I'm going to move my E1 for a second. Because it makes a carbocation. And it's a secondary carbocation, so it can rearrange. So then it moves down here, right? That methyl, the hydrogen here will shift up. And now, right, you can treat your carbocation as your alpha carbon. Have beta 1, beta 2, beta 3, right? You're going to make your double bond now to the beta carbon that has the least hydrogens. You're going to follow Zaitsev's rule now that you've done your rearrangement. And that's going to make this. What am I doing for this next one? What kind of reaction is it? It's not substitution, right? So LDA, if you remember, right? It's a big charged base, right? It's one of our two big bases. So it's potassium tributoxide and LDA. So this is going to be an E2 reaction because big bases, potassium tributoxide or LDA, can only do eliminations and they're charged, so it's an E2. And big bases always make the least substituted double bond that they can. So the product I'm going to get is that. What kind of a reaction am I doing for the first one? Zoom got it. It's SN2. Secondary halide does anything, right? NaCN, Na, sodium, has a metal, so it's charged. So you're to the 2s. And then 0 degrees is cold. So SN2. So we've got to add a CN. And it needs to be up because my leaving group was back. What is the last one? Secondary halide can do anything. Got a sodium again, so it's charged. Minus 78 is really cold, so it's SN2 again. Fun fact, SN2 is the most often used cold temperature in organic chemistry because that's what temperature you get when you mix dry ice with acetone. I guess one more for the road, maybe. What kind of reaction are we doing? E2. Secondary, charged, to get you to the 2s, high temperature elimination. So alpha, beta 1, beta 2, they both have the same number of hydrogens on them, but which one am I going to make my double bond towards? One of the hydrogen in the back, which is B2. Yep. So there you go.
I was asked why I got rid of the wedge on the carbon that I had on the double bond, but kept the dash on the beta 1.
Yeah, because so you don't put wedges and dashes on double bonds. Double bonds are always flat. So when you make the double bond to beta 2, it no longer is pointing at you or away from you. It's in the same plane as the page. So you always lose your wedges and dashes on double bonds. Sure. And I think that is that. Exam will open up at 8 a.m. on Friday. You'll have an hour-ish to complete it. I got to see exactly how long it takes me, but I think it'll be an hour for you to take it. So you just need to find an hour sometime between 8 a.m. and basically 11 to start it. And then you have till midnight to finish it.